All right, starting from the previous lecture, do you have any questions, any comments that you want to make? Let's start with those if you have any such questions. Because if you don't have any, we will continue with the convolution from a different perspective and give examples to that different way of making convolution implementation. Here, first, we started with the meaning, the understanding of convolution. That is critical because in many places, if you just check the internet, you will notice that even the books themselves are explaining the concept of convolution just as a technical way of making a calculation. That way of making calculations, we will see right now. But there's actually more to that. The convolution comes from the concept of linear systems. And in the linear systems, we have the input, which can be decomposed into impulses. And we will, one by one, find the impulse responses for those split impulses, different impulses, and we will combine those impulse responses. That is the formula that you see on the screen. That is in the red box, in the second red box, the last one. That's very critical way of understanding where that convolution comes from. But once you have the formula, this formula, it's easy to apply it. There are methods to find the convolution. The example that we saw here and the way that we approach the problem and solve the question is actually not the practical way of solving it. There are some easier implementations for this one. We will see those implementations very soon. Yeah, so if you don't have any questions, then we can actually start with the way of making an implementation of convolution and start looking at it from a different perspective, just technical and methodological way of implementing that one. And it's like this. First, let's write the formula again, once again. Y of n is the convolution of x of n and h of n, which is this infinite sum, x of k, h of n minus k. H of n minus k are responses of to delta n minus k's, the shifted impulses, and xk's are the scale, and we are combining with the summation. Now, a different way of implementing this is by thinking everything on a different axis. Let's call it the k-axis. Okay, because at the right-hand side of the equation, as you see, we have the index k. And so what does that mean in the k-axis? Actually, the k is not an axis. We don't have a function of k. So it's a little bit confusing to reimagine everything. And now let's assume that k is the axis. Then we have, first of all, x of k on the k-axis. This is inaccurate. I'm sorry to say that, but it's just the way that we implement. But once we understand the implementation, you will understand it very well and you will memorize it that way. It will be very automatic, don't worry. Let's think of an easy example. Let's say that the x of k is this, okay, 1, 2, and 3, at 0, 1, and 2. This is x of n over n. So x of k will look the same. This, and this. Simple toy example. And then I will have an h of n, which is even easier because this is just a toy example, as I say. It is 1 and 1. 1 and 1 at 0 and 1. Now, how can I draw h of n minus k? It depends on what we choose as n, of course. for some various values of n, it will look different. So let's start from n is equal to 0. If n is equal to 0, for instance, so n is equal to 0 case, what does h of n minus k look like? Then it will be h of minus k, because it will be 0 minus k. H of 0 minus k is h of minus k. So what is it? H of n is this. H of minus k over the k-axis, of course, is the folded version, flipped around version. So let's flip around h of n. It is 1, 1 at 0 and 1. So if you flip it around, it will be, again, 1 and 1, but it will be at minus 1 and 0. So it's going to be like this. Do you agree with this? Formula, the convolution formula. I am multiplying x of k with h of n minus k. They are multiplied. So let's multiply them. Let's multiply these two signals, x of k and h of n minus k. Their multiplication will be here. X of k times h of 0 minus k. And it's going to be only this one. Do you see that? Because when you multiply these two signals, they overlap. They overlap at a point. One of them is here, and the other one is here, and they overlap only at this particular value. There's no further overlap. So when you multiply them, you will only get the corresponding multiplication of the value of x of k at k is equal to 0, and h of minus k again at k is equal to 0, which are both ones. So multiplication of 1 and 1 will give you 1, and that's it. The others will always be multiplied by zeros. For instance, this times this 0 here will be 0, so we don't have anything. Let me therefore erase that. Okay, this is the multiplication. And from here, let us sum all of this here, all of the signal x of k times h of 0 minus k. Let's sum them up for all k from minus infinity to infinity. What is the summation? What is the accumulation or area under this function? Let's sum them up. It is 0 plus 0 plus 0 plus, etc. Only at 0, we have 1 plus 1, therefore, plus 0 plus 0 plus 0, etc. So what is the sum, accumulation of this signal that I have drawn? It is equal to 1. Now, what is this 1? I tell you that this is y of n at n is equal to 0. Why was n is equal to 0? Because I chose it this way. When n is equal to 0, h of n minus k looks like this. It looks like h of minus k. And the thing that the value that I find at the output is the multiplication of that h of minus k with x of k, which is the last graph, and I sum them up, it gives you y of n at n is equal to 0. Now, I am going to erase these last portions. So you may want to take screenshots, or I'm also starting to distribute the videos. The previous videos are already available on my YouTube channel, if you have noticed, as well as all the previous lectures, of course, but this year's videos are already there, so you can find them. You may want to rewatch, or if you're taking notes, be careful about this, because now I'm going to erase the last two graphs and the last things that I found, except this formula. So I'm erasing. especially this part. And I'm also going to erase this. I'm going to erase this and these portions as well. Because the next thing that I want to do is I will take I will again draw h of n minus k, but this time for a different n. Do you think it's reasonable to draw for n is equal to -1, which will make h of -1 minus k? So since it is h of minus k, it's the flipped around version of it, but this time it is shifted to the left further by 1. So we flip around this h of n, and after flipping around, shift further to the left, which will give me this. Okay, it's fine, 1 and 1 at -1 and -2. But the problem is that I have to multiply h of n minus k with x of k. And when I multiply these two signals, notice that there is no overlap. Therefore, their multiplication will give you zeros everywhere, right? Since it is zeros everywhere, its accumulation, its summation is also 0 because there is no overlap and everything was 0. So y of n for n is equal to -1 would be that summation of all zeros, which will give you 0. What would happen if I further shift everything to the left this way? If I shift the signal further to the left, it will remain that way. There will be no overlap between x of k and h of n minus k. Therefore, their multiplication will always give you 0 because there's just no overlap. So if you further go towards left, I will get y of, y of n for all n less than 0 will give me a 0. If I shift to the left, it means n is less than 0, like -1, -2, -3, etc. So they are there. That is therefore the boundary of our information. The 0 point was the boundary that we found where y of n at n is equal to 0 we found to be 1. That was the first value. To the right of that, we will have overlaps. To the left of that, we don't have any overlaps. Therefore, this is not a valid or not an important or critical thing. So we have to start thinking of other ends. Let's go to the right-hand side. We have to adjust the shifts to the left and right in such a way that x of k and this h of n minus k just overlaps for that n. You have to think of it that way. So sliding to the left, we have no overlap. Let's slide to the right. Let's make n is equal to 1. And then this will be h of 1 minus k. H of n is, or h of k is made h of minus k by flipping around. And then now we shift to the right by 1, which will give you again the same shape, essentially. 1 and 1 at 0 and 1. So this is h of 1 minus k. I flipped around and I slide it to the right by 1. Sorry. Now, what kind of an overlap do we have? We have to multiply x of k with h of 1 minus k. And their multiplication will be at the overlapping positions. The overlapping is at 0, where this 1 here is multiplied by the corresponding positions 1, which will give you 1. And then this 1 value will be multiplied by the corresponding positions value, which is 2. So 1 times 2 is 2. So this is x of k times h of 1 minus k. And after that, I have to sum them up for all k over the k-axis. So I have to sum up all of these values, 0 plus 0 plus 0 plus, etc. Plus 1 plus 2 plus 0 plus 0, etc. So it is 1 plus 2, which is 3, right? So what did we get at this point? We found y of n, oops, not k, so y of n at n is equal to 1 is equal to 3. Okay, we found this. Previously we found this, and we also found that it's all zeros before. Okay, so we flipped around and slided to the right. We obtained 1 and 2 values as a multiplication, and we accumulated all these, and we found 3. Now I'm going to erase them because I want to slide to the right-hand side once again. So I'm erasing all of this one. And this one too. And these values, and this, and this. So now let's shift again one further to the right and make n is equal to 2. So h of 2 minus k. What is it? It is the flipped around version of this h. And shift to the right by 2. And it will be this and this. And sliding one by one at 1 and 2. Now, what is the multiplication of x of k and h of 2 minus k? Let us multiply them. 1 and this 0 in the center will be multiplied to obtain a 0. And this 1 times 2 will give you 2, right? And this 1 times 3 in the corresponding position will give you 3. And afterwards, it's 0 times 0 everywhere, so we have nothing. Now, in order to find y of n at n is equal to 2, we have to accumulate or sum this x of k, h of 2 minus k signal, sum them up, sum up all the values, or find it, it's like finding the area. So it's 0 plus 0 plus, etc., plus 2 plus 3, which is 5. So y of n at n is equal to 2 is equal to 5. And then we have to slide again to the right, so I am erasing. That's why we need a kind of an animation for this. That would be a good one. I'm erasing this, and I'm erasing this. I'm gonna make them this time 3. So it's going to be h of 3 minus k, which corresponds to flipping around and sliding 3 times to the right-hand side. That will give you a 1 at 2 and another 1 at 3. And the others are zeros. And when we multiply them one by one, this 0 will be multiplying 1, but it's going to give you 0. So this 0 times 2 will give you 0. So we have 0 here and 0 here. And 1 times 3 will be 3, like this, at 2. And this 3 will be multiplied by a 0 here. So it's going to be again a 0. So we are multiplying as long as they overlap. They overlap at some points, and after some points, they start not overlapping. For example, what would happen if n is greater than 3? Let's say it's 4. Then it's 4 times shifted to the right, which will fall out of the range of x of k, so they will not overlap. And since there's no overlap, we know that starting from 4 and onwards, y of n is equal to 0. So this time y of n at n is equal to 3 is the summation of this signal from -infinity to infinity for all k's. And it will be all zeros except at k is equal to 2, which will give you a value of 3. So this is equal to 3. And afterwards, y of n for n greater than 3 or greater than or equal to 4, it's all going to be zeros. So we don't have to erase the last one because this is the last one. It was the last slide. But now I want to plot y of n. It's all zeros for negative n. I am plotting y of n. At 0, y of n was 1, like this. And at 1, its value is 3. At 2, its value is 5. At 3, its value is again 3. And starting from 4 and onwards, it's all zeros. So this is the convolution output. Now, what kind of technique did we use? We used a technique called folding and sliding and finding the overlapping multiplications. It's fairly simple. We just flipped around h of n, or this one, and slide it over x signal. We plot the x signal like this. We fold this, and draw it on top of that one and see what kind of an overlap it makes. And then we integrate or we sum up the overlapping regions. That's the methodology that we applied. I found only one relatively useful kind of a video from YouTube. So I want to actually show that YouTube video to you. Since I will be using the whole video, I hope that the guy who made that video as the animation wouldn't sue me or want me to remove the video from YouTube, which also contains these informations. But that animation is one of the things that I was able to stumble upon in the on the internet, and it's here. This one. Sorry for the music because it also has some kind of audio, which we have to incorporate somehow. So it looks like this. I want to show this one to you. If it loads. I was able to load it, but now it's just rotating. Or maybe I can give you the address or which one from the list of YouTube videos, because obviously I am unable to start. Yeah. So as you see, it's the it was the formula. If you can just catch it, it was very fast. Yeah, but this formula that you see is summation xk hn minus k for all k. That is the convolution of x of n with h of n, as we have discovered. Let's grab it. This is an example x that is used, and this is an example h. So it flips h, as you see, and from -1, as you see, there is nothing overlaps. So y of minus 1 and everything negative is here. But at n is equal to 1, there's an overlap, and it accumulates the overlap to find the point. Now it overlaps again, shifting one more to the right, and it finds the y. Shift again, 3 overlapping things, multiply those, and then at the top you find y is equal to 6. 3 plus 2 plus 1. And then shift again, some different overlap, those overlapping from them. Shift again, something still overlap, and we combine those multiplication overlapping things. We first multiply, and then shift again, still overlap. Now shift again, now nothing else. Therefore, starting from n is equal to 6 and onwards, it's just nothing. And these are the values of y. Let's plot them, and it will give you this kind of a shape. Okay, that's a kind of an animation that I was able to find on the internet. You can also find it, I guess. It was named Digital Signal Processing Convolution by Connie. Yeah, that's what it was that I want to show you. So let's come back to our page. So the method is clear. You flip it around, you fold it, and then you slide to the left and to the right. As long as they overlap, they correspond to an output. And the amount of sliding is the position of your output, or the value of your output at the corresponding n. If you slide by -1, it means you are finding y of -1. If you're sliding by 2, it means you are finding y of 2. All right? Be careful about these. So that's how we find the discrete time convolution normally, flipping and sliding. Now, many students fall into example traps because you don't usually exercise with actual problems from the book or from other resources. So in the examinations, you fall into a trap of simplicity. And that simplicity is because in most of the cases, one of the signals are all ones like this, 1, 1, 1. And whenever they are like this, you start imagining that every time you slide and you multiply, actually you come up with the value, with one of the values, which is already 2 here or 3 here, as you see. Because the previous values that you fold or whatever are all ones. Actually, they may be also any kind of a numerical value, a real number that you may have. It may be pi. One of them may be pi, the other one can be 1.5. So their multiplication will be 1.5 times pi. Okay, 3 pi over 2, in other words. You have to, one by one, multiply those values. Since all of the examples have one of the values to be equal to 1, I have noticed this from previous years' students. They don't even multiply. They take one of the signals and then they accumulate because the other multiplication value was always 1, but it doesn't have to be. These values could be 1.7 or 2.1 or pi or e, you know, those are some real numbers. They don't even have to be rational. And whatever they are, you must multiply with the other corresponding positions, value of the other signal. The signal's values are multiplied. They don't remain as it is, okay? I know that what I'm saying is maybe not so critical because, of course, I'm telling you that you are multiplying, but you forget after some time. That's why I'm insisting on these. Now, I want to give another example, which is an infinite way of making convolution, like this. H of k, the impulse response, which you are supposed to flip it and then start sliding. But the previous examples were finite length signals, starting at some point and ending at some point. Whereas this one is a unit step function, which continues to be just ones forever, starting from 0 and onwards for all n. So, oops, it's not h of k, it's h of n, I mean, sorry, h of n. So h of n is u of n. The impulse response of the system is just staying as it is. It does not decay or explode or end at any other position. The impulse response stays as 1, starting from the impulse position of 0. How will you attack this problem for a given another x of n that I want to give to you, which could be given as an analytical expression like this: x of n is equal to e, not e, it's alpha to the n u of n. In fact, I didn't even have to draw these things. In a question, I could say that h of n is u of n and x of n is alpha to the n u of n. So as you see, x of n is also infinite extent. It's an exponential, alpha to the power n, starting from u. Depending on the value of alpha, it could be an increasing exponential, like if alpha is greater than 1, like 2 or something, it will be an increasing exponential. Or if alpha is less than 1, like between 0 and 1, like 0.5 or something, then it will be a decaying exponential, right? But it's infinite extent still. For instance, it essentially looks like this for a stable kind of a behavior over n. It starts from 1 because alpha to the 0 is 1. Anything to the 0 is 1 actually at 0. But for n is equal to 1, it will be alpha. At n is equal to 2, its value will be alpha square, and then alpha cube, then alpha to the 4, etc. So it will be a decaying exponential kind of thing at 0, 1, 2, 3, 4, etc. For everything before 0, all the values before 0, it was the value is 0. Because of multiplying alpha to the n with u of n, I deliberately cut this exponential from 0 and make it only to the right-hand side, a right-hand sided signal. So we have these two signals now. And how do we convolve these signals? And can we come up with an analytical expression of y of n? I'm not only saying plotting, but I want you to give me an expression of this thing. But it will take some time, and we are already utilizing a lot of minutes. Normally, the university asks from us to keep it like 20 minutes or between 20 and 30 minutes at most. But we are doing a little bit more than 30 minutes, but that's fine. We are mature students, and I'm asking you to keep your focus throughout the course. But still, this is enough. So I will stop at this point, but I will give you this one as an exercise or a rumination question where you have to think about it. Try to visualize what happens if I flip around h of n and slide it on the other one. What kind of outputs will accumulate? Okay, it will be summation of some numbers. Those summations will have analytical formulas from series, power series that you have seen from in calculus courses. So it's a finite power series sums after flipping around and sliding, some of these alpha to the number k values will be added for some certain k's. So what is that summation? Can you write the formula for that finite power series summation? That will be the expression for y of n, right? So think about it. We will do this, but on Wednesday. So I don't want to proceed further with the solution of this one. We will do it on Wednesday. You may start thinking about it. Doğukan asked if alpha is less than 1. Yes, you have to take it that way. Otherwise, those summations will diverge. It will not be a stable system. And if it is not a stable system, it's very difficult to find analytical formulas for unstable systems. So let's assume that alpha is between 0 and 1. Let's forget about the negative alphas too. I mean, it may be -2, for example, which is another unstable system. Yeah, but yeah. Visualize it like this, like the one that I have drawn. It's a decaying exponential, so it's between 0 and 1. Okay, I'm going to stop the recording now, and you may have some questions you may ask.